Thank you so much, Mr. John. I'm very glad to be here with you. I will introduce myself first. My name is Abeer, Olayan, and I'll tell you something that I really found a hard time when I pronounce my name here with the people in the US. They found my name is very hard to pronounce, and every time they ask me how we can pronounce your name. So I just told them, just imagine that you want a bear. Let's have a bear. And this is my name. So that makes things easy a little bit. So I will give you a background about myself. I was working with the MAM University for 12 years before joining Saudi Aramco in 2011. So I worked with different teams in Saudi Aramco with XPIC ARC, XPIC Advanced Research Center in upstream, working with reservoir team, geochemistry and drilling team. And now I'm the team leader of Chemical Development Initiative in Saudi Aramco. This initiative started since 3 years, and it's aimed to develop the chemicals, new chemicals in Saudi Aramco that targeted the oil and gas operation for upstream phase. So maybe I will give you some ideas or some introduction about what is the product development through my presentation. But let me first brief you about this program that we are involved in it, but from Aramco side. So in June, as John said, in June 2012, the MIT former president, Susan Hockfield, and Saudi Aramco former COO, Khalid Al-Falih, signed a memorandum of understanding in Dhahran, Saudi Arabia, providing a framework about greatly expand the education and research between MIT and Saudi Aramco. Khalid Al-Falih announced at the same agreement Saudi Aramco's plans to have our Aramco Center that located in Cambridge, in the Technology Square. And at the same agreement, they announced the enhancement of Bin Khaldun Program Fellowship for Saudi Arabian women. This is under the Clean Energy and Clean Water Center, and with collaboration of KFUPM and different Saudi universities. So this 5 years program, having from 5 to 10 fellows every year, and try to cover different fields from engineering to science to architecture. So I joined this program in 2015, September 2015, joined Dr. Alfredo Katz, Alexander Katz group, who's working with material science and engineering department, and who is interested in fundamental understanding of self-assembly, the dynamics of soft materials and polymers in novel applications such as biology, medicine, engineering, chemistry, and physics. So we came up with different ideas about developing smart materials to resolve our challenges in oil and gas applications, taking the inspiration of medical and biological side. And you will notice that I'm not just consider one idea for just one specific application. I try to have or to cover the different ideas and different application in upstream. So the first project that we already achieved is try to develop a new shear thickening based on nanosilica particles, and this will be for numerous application in upstream, and I will explain it more in the next slides. The second idea is to develop nanoparticles, polymer grafted to nanoparticles that will increase the oil recovery, the oil production. And this actually, it's not a silica particles, it's a gold nanoparticles that they use it in treatment of one kind of cancer disease, But sure, we will not use the nano gold particles in oil operation. We will not throw the gold to bring out the oil. It's not deserved. So we will try to replace the silica. And why silica? Because silica is the major component of local Saudi sands, which is available in Saudi Arabia, and which is aligned with product development strategy in Saudi Aramco. So the third idea is self-healing polymers for cement, as a cement additives. So we will have a big achievement if we can develop a self-healing polymer that can resolve the biggest challenges in cementing job. So now I will talk in details about the project that we have achieved about new shear thickening based on silica particles. In oil and gas operation, in order to have thick fluids to increase the viscosity of the fluids in operation, so we have 3 or 4 methods to increase the viscosity of any fluid, either by increase the concentration or by increase the molecular weight. Another approach is to introduce a charge moieties along the backbone of the polymer. These charge moieties will increase the electrostatic repulsion between these charge moieties and will increase the hydrodynamic volume of the polymer and then increase the viscosity. The new approach now is to introduce hydrophobic groups in the backbone of the polymer. So these hydrophobic will interact with each other when any high shear or high force will apply and then will increase the viscosity. So the fourth approach that we have used. So shear thickening fluid, or shear thickening material is a new nanotechnology that moves like a liquid and then it behaves like a solid in a few milliseconds when it counters any force or any shear stress. And this is the opposite of shear thinning, like paint, which is become thinner when you paint it or when you stir it. So it's the opposite of shear thinner. The famous example about shear thickening system is cornstarch, which you use it in cooking. We use it in drilling in our operation. As you know, cornstarch is a liquid. If you stir it slowly, it will still liquid. But if you hit it on the wall, or even if you walk on it, it will solidify. So shear thickening now have a potential application in industry, in different industry. We have a lot of products having the shear thickening material. And the famous products are the body armor, the helmets, the gloves. And why? Because shear thickening can form fabrics that could be resistant to any penetration. So the transition between a flowing liquid to a solid-like material is due to forming hydroclusters between the different particles that will dramatically increase the viscosity. And this is a reversible transition. So as you can see here on the left side, this is the sample in normal situation for the shear thickening sample. As you can see, it's a liquid, and the one on the right, after shaking the same sample in horizontal direction, as you can see, it's transformed to a gel, and this is the corresponding structure model. As you can see, it's transfer from a separate flux to three-dimensional network shear fields. So in this invention, we take the inspiration from the medical industry, mimicking the dynamic of the biopolymers in a blood clotting cascade. And here is how the process works. In the equilibrium, the colloidal fluid suspended have a tiny particles that repel each other. This is an equilibrium situation. After applying any shear on any force, these particles will stick together and forming lines that will form a gel. And this is, as we said, a reversible. So when you remove the force or the shear, the fluid will transform again to the liquid side. Okay, so this is the project team. Maybe my situation is a little bit different because I try to involve Saudi Aramco Center with Dr. Alfredo Group. So we have different names from MIT and from Saudi Aramco team. And our objective here is not just develop a normal shear thickening, but to develop a new shear thickening that will have a characterization and will be resistant to a high temperature and a high pressure. In addition, the unique chemistry of this shear thickening supposed to make it applicable for different applications, not just for one application. So this is, for a business purpose, this is the timeline for our project. As you know, any product development process should go through 3 phases. So we try to put a plan for these 2 phases, and we leave the 3rd one when we try to start to commercialize this product empty to waiting to see the implementation result when we start to try this material in the real field. So this is a brief about the chemistry of how we synthesize this material. The silica nanoparticles is functionalized with 2 kinds of polymer, one with long chain and the other one with short chain. So the long chain will leave it free, and the short chain will functionalize it with specific functional group and using materials like histidine. And why histidine? Because histidine have the ability to form a very strong hydrogen bonds that will be stable. So in normal state, this long chain will form like a shield for this histidine group. But when we apply any shear stress, this long chain will be aggregate, making like a window for the histidine group in the short chain, and this histidine group will start to connect with each other. So when you remove the shear stress, the long chain will be relaxed again and covering the histidine group. So this is the mechanics, how this reversible process works. So this is the synthesis in details. I will not go through it. And this is the results of our test. As you can see, here the proposed shear thickening try to viscosify with high temperature. So as we increase the temperature up to 100 degrees, the viscosity is increased up to 100 centipoise with shear rate around 450. And this is an excellent result because, as we mentioned, our aim is to develop a shear thickening that can work in harsh environment such as a high temperature. So this picture shows our sample, our real sample. Unfortunately, this is supposed to be a video, but it doesn't work. So yes, it's work. Excellent. It doesn't work before. So as you can see, it's a liquid, but it's not sprayed in the tube as a normal liquid. It's like a bouncy ball moving together. It's a colloidal liquid. And here is the microscopic video for the particles and how it moves in this shear thickening. As we said, the particles are repel each other in normal state. So we try to did something to stimulate or to force these particles under the microscope to see how it works. So we try to stimulate it by a needle. We brought a needle and just maybe teasing this liquid. And as you can see, the particles stick together. And this is what we mentioned before. It's not sprayed again, and that means this is a shear thickening. Okay, this slide shows the different applications. This is just an examples of application. We have more applications that we can apply, and this is just some of them. As you know, in oil and gas operation, the unwanted flows while drilling could maybe damage the wells or reduce the productivity of the well during, such as produce or maybe loss of a production hydrocarbon, increase the cost and the dangers of the wells. So in order to use this material in applications such as loss circulation material, what is loss circulation? Loss circulation is happening while drilling. When we drill a well, we use a fluid, we use a mud. So sometimes we face fractures, like these fractures, that will lose the fluids to these fractures, and you will having stuck by the stick of your driller. So this is a very challenges problems that we have in our operation. So in order to overcome this challenge, we try to develop materials that can plug these fractures, so we can continue the work and drill more distance in the well using the fluids. So this shear thickening can use for this purpose. We can use the shear thickening to plug these holes, and in order to do that, we need to stop the reversible reaction, because as we mentioned, the reaction is reversible. So in order to do that, we tried to add different chelating agent like copper, and we found that with copper we can hold this gel and form a very stable bonding between the copper and the imidazole group in the histidine. I will show you a microscopic video. Oh, it's not here. Okay, I'll try to show it to you in my file. And how is these particles? Okay, the shear, yes, with copper. So this is the shear thickening after adding the copper. As you see, it's a stable gel, and this is the particles now stuck together and forming a very stable material. And in this case, we can use this material as a loss circulation. It's not a reversible, it's a irreversible process now. Okay, another applications for this shear thickening material, we can use it as a blowout preventer. Also, another challenge we have when we drill, that we can face a gas cap. So this gas cap could make an explosion while drilling. So to avoid this, we use this shear thickening. So when it faces the gas cap, it will transfer to a gel, and it will hold this gas and prevent the explosion. Another application, we can use it as a cement additive to delay the hardening of the cement. Also, we can use it as additive to the water when we start to produce the oil. So when we produce the oil, we inject the water from the injector well. And as you can see, the water is lighter than the oil. So we have a problem of fingering. When the water starts to pushing the oil, the water starts to have like a fingering problem. So we add sometimes a polymers that will increase the viscosity of the water to be equal to the oil, so we can push the oil from the well and produce it. This shear thickening can replace the conventional polymers and can use to increase the viscosity of the water to increase the oil production. So this is the forward plan for us. I choose the background picture because we are talking about silica, and the silica is the major component of the sand. And I found this nice picture for camels because maybe I missed the camels here, maybe. So we will try to improve the material with the time, and 3 patents now in the process. We are writing 3 patents for different applications. Maybe we will have more in the future. So the second project, I will just give you a brief about this project. We started now to put the concept, the ideas about how we will start to synthesize the cement, the self-healing polymers for well integrity. Cut your finger while chopping the onion and you may cry, but with a little care, your wound will heal itself soon enough. So in this project, we try to mimic the healing ability of this biological tissue and to try to investigate the potential to synthesize the same. So self-healing polymers is a material that could heal itself when any damage can occur whenever or whatever happened on the material. In general, there is 2 kinds of self-healing polymer. There is an extrinsic self-healing, which is a material that you added to the material that it already damaged and as a healing agent. And most of the service companies that Aramco conduct providing this kind of self-healing to avoid the damage that's happening in the wells. So they always provide the extrinsic self-healing. Another kind of the self-healing is the intrinsic self-healing, which can heal itself when any damage can happen through the chemistry nature of these materials. So we plan to develop this kind, which is intrinsic self-healing material that can heal and seal the damage that will happen in the well and that could trigger the temperature, because the most challenges that we have in our wells in Saudi Arabia is the high temperature. The temperature can reach to more than 200 centigrade, and the pressure is more than 2,000 sometimes. So the main application for this is to cure the cement sheath damage. Cement sheath damage can happen when we drill the well. I will give you how this works before I continue. When we drill the well, we try to add the cement just to casing this well and make it ready for the oil production. So this stage of adding the cement is the critical step for our operation, because you could have cracking on this cement if it's not very qualitative. So we try to add, to develop a self-healing polymer and mix it with the cement, so any problem, any damage can happen to the cement while casing, this polymer can resolve it. So why the damages can happen to the cement? It could happen while drilling. It could happen when we are perforate the well. After we adding this cement, we start to perforate it to make a holes in this well by guns, like it's like guns, and to make a holes to start to produce the oil to the wells. So perforation can make a damage for the cement. So this material will resolve this problem. We have tools we already use in cement job that could just prevent this damage in the cement placement. But the self-healing polymer can be effective from the placement, starting from the placement of the cement until the end of the well life and into the abandonment. So this is just an overview about the second projects. Maybe we can update you next time. If I stay for the next year, I don't know. So this is my presentation for today. I would like at the end to thank the Center of Clean Water and Clean Energy, Professor John, Professor Kamal, Kate, and Teresa. Thank you so much for all the support that you provided to me. I would like to thank Dr. Alfredo Katz and my group for their support. And sure, I would like to thank Saudi Aramco management to gave me this opportunity to join Bin Khaldun program. Thank you so much.
Other questions?
I believe there is a lot of questions because we go through the oil and gas operation, so it's supposed to be a lot of questions.
I'm going to call on someone for a question. Ahmed, do you have a question?
All right, I'm being put on the spot. So do you have any sense of the comparative value of these technologies in Saudi Arabia?
Yes, actually, as I mentioned, the product development initiative in Saudi Aramco was started to replace the products that we already imported from the service companies, which is most of them are foreign companies. It's not Saudi companies. Let's say 90% of our material is provided from these companies. So Saudi Aramco decided to replace some material, to innovate some materials that will resolve our problems, because nobody will understand our problems like us. So we hope that this material will impact the most challenges that we have in our operation. So as you see, the first product will cover a lot of applications that will save money for Saudi Aramco, that will save the damage that could happen, that will replace material that we imported, avoid the shipment, avoid the storing, and all these logistic process. So yes, it will add a value.
This is a great idea that self-sufficiency has to be done by Aramco. But any product or any material which you produce at a lab scale, before you take it to commercialization or real application in the real world, what you are talking 200-degree and high pressure,
Yeah.
you have to make a lot of tests. First of all, this is a big challenge.
Yeah.
The second is that how to produce this material at a large scale. You need a lot of, I think, engineering and technology. So do you think this is possible with Aramco?
Yes, sure. We started this plan since 2013, and we try all these years to put a plan how we can gradually develop our materials. So we believe that the scaling up is very important and critical step. We have different plans for scaling up the materials gradually and try to test the different conditions. In our center now here in Boston, we have small, let's say, pilot plant for scaling up just a little bit amount to test the conditions like high temperature and high pressure when synthesize this material. And we have in Dhahran, an R&D center with downstream, we have 10 pilot plant facilities in the building. So we will try to scaling these materials and test the different conditions to make that this material will be safe when we move to the pilot plant manufacture facilities, the huge one. So we will try to scale up this material, taking the support from Saudi company. we will try to stimulate the industry in Saudi Arabia to be aligned with Saudi Arabia vision, 2030 vision, to stimulate the industry, to create jobs, and to maybe localize the companies. Maybe we can attract the companies, the foreign companies, come, bring your manufacture facilities to Saudi Arabia, and this will stimulate the industry. Yeah, you're welcome.
Yeah, it's a very exciting thing to see the shear thickening here. But shear thickening may be a trouble because you need to deliver to the location, then it should become shear thickening. So
Yes.
I would say at the beginning it should be shear thinning, then
Yes.
transition to shear thickening may be necessary. So if you design, can you design that kind of a
We need to know what is the shear rate. So once you know what is the shear rate that your material will transform to a gel, you are in safe time. So we will know what is the exactly shear rate that will make our material start to solidify, and we will do the same in the well, because we can control the shear rate in the well. Our shear rate reached to 600, so we can control it.
What if, I mean, when it goes down, I mean, temperature goes up. So can you make it, I mean, it's a very exciting material, but also it can be triggered when the temperature goes higher than some number, then it can become shear thickening. So so
when it's go down, we will control the shear rate and the temperature. So we know the temperature downhole. So we know in that temperature, this shear rate, shear thickening will transform to a gel. But if it's, for example, if I understand your question, this shear thickening transform to a gel, and we don't want it to become gel right now, in this time, we can resolve this problem using different chemicals that could resolve, maybe melting this material or control the pH, for example, to change the nature of this material. So we can control. Yeah, the temperature is the first parameter that we need to control. Yeah.
Good. We have for you as well. Is that?
Asma. Yeah.
Asma got one, the previous.
You already have one.
She's a senior member.
Okay, thank you so much. Thank you.